So again, we look at band gap because we want to be somewhere in this part to take advantage of the sun. We talk about silicon. We talk about the periodic table. And a lot of the calculations, when we talk about Schrödinger's equation, these are really energy calculations, okay? And in the discussion, we look at doping silicon with phosphorus, doping silicon with boron. Why will we not dope silicon with aluminum or with arsenic? Could we dope silicon with aluminum and arsenic? In theory, yes, okay? And how do we know that it's going to work? And let me give you an example of what it takes. If you combine, if you have this, if you have a, so what happens if you combine hydrogen with oxygen? If I have gas, hydrogen, oxygen, oxygen in gas form, hydrogen in gas form, and I mix them, what happens? Water, okay? Plus what? A lot of energy, a lot of heat, a lot of energy, okay? Okay? So if I have a system and I have gas, and liquid, what is the most stable configuration? If I have all these compounds at room temperature, what is the most stable configuration? Okay? Remember, this is in an unstable condition. This is a stable condition. At room temperature, these are in an unstable condition. You mix them, they reach a stable condition. And this is how much energy is extra keeping the gases in a separate form. So nature is going to tell you how much. Now, you can do an experiment in the lab to see how much energy it takes, but you can actually do this calculation, and you can find how much energy is needed. Now, if I have water, and I want to get can this reaction happen spontaneously? No. I have to add energy, okay? And I can do this calculation. So going back to the question, could we dope silicon with aluminum or gallium or arsenic? The answer is yes. In some cases, it's going to work. In some cases, the boron is going to be in a stable condition, the phosphorus. And you can find that there are some elements that do not like to be with silicon. It's going to take a lot of energy for you to dope the material, and it's going to be in such an unstable configuration that nature is going to tell you he doesn't want to be doping that element. It's going to move out, okay? So when you do these quantum mechanics calculations, what you are doing are really energy calculations. And these calculations are going to tell you whether or not a compound can form and how much energy it's going to take to make that compound, or if it's stable or unstable or metastable, okay? That's really what you're doing with quantum mechanics. You're doing calculations, and it's based on stable configurations. When you do DFT calculations, what you do is you are finding the most stable configuration. I mean, it really boils down to that. That's the equivalent of doing those calculations. So we talk about this. We talk about this. We talk about band gaps, valence bands, conduction bands. We saw this in the video. So let's see what type of systems people are interested in. We talked about this on Monday briefly. So this is a chart that shows the efficiency, in percentage values. This scale goes from 0 to 50% efficiency. And this is a historical chart. These are the most recent results up to 2015. They start here in green. RCA, this used to be another famous research laboratory, RCA. Do you remember RCA? Was a company that make electronic components, RCA. So that's what these labs come from. And these data are organized by color, and the color code is right here. So let's start first with crystalline silicon, which are the blue symbols. And for silicon, there are many variations. You have single crystals with a concentrator. So what people have done very effectively is that you can put like a Fresnel lens on top of the cell to concentrate light, okay, and increase intensity. And those are these ones, these single crystal concentrators. The problem with single crystals is that very expensive. To make single crystals, it takes a lot of money, a lot of energy. So these cells are very expensive, these single crystal cells. And obviously, they show some very good behavior in these cases, but again, they are very, very expensive. You have these multi-crystalline systems, which are not as efficient as the single crystals, but they are less expensive. You have thick silicon films, and you can see the trend for silicon. So in the case of silicon, you are not going to exceed 30%. That's a theoretical limit for the efficiency of silicon-based cells, about 30%, okay? That's the best you're going to do with silicon, 30%. Then you have these so-called thin film technologies in green. These include these copper, indium, gallium, selenide. They are so-called SiGs. And you can see how they've improved efficiency as a function of time. These are cadmium telluride, the ones with yellow. Okay, these are thin film technologies. And again, you barely make 20%. The advantage of these thin film technologies is they are less expensive than silicon. The reason being that you are only using a relatively small, thin layer of material, so making these cells is less expensive. And obviously, the best results to date are obtained with these multi-junction cells. And the idea of the multi-junction, as we had seen, is that you stack cells, and each one captures a different part of the spectrum. And they continue to increase. The efficiency of these cells is greater than 30%, which is the theoretical limit. And the reason being that you are really combining the operation of multiple cells, and we expect this to continue. The disadvantage of these systems is that they are very expensive. Okay, you have to make several layers. And people now are looking at adding thermoelectric materials at the bottom to capture some of the heat and to further improve efficiency. So in the case of silicon, the bulk, if you buy panels these days, the majority of them are made out of silicon. Remember, you need a PN junction. You need a current collector on the bottom that is usually made out of aluminum. You have your electrical contacts in the front to close the electric circuit. You have radiation. Most of these cells have an anti-reflective coating. And the reason to do that is to minimize losses due to reflection. There's a lot of work using nanotechnology to develop these anti-reflective coatings. Here is your PN layer, and that's your standard silicon cell. Same thing with amorphous silicon. They are less expensive. The efficiency is not as good. It's only 12%, but the cost of this is much lower. Cadmium telluride. One of the concerns with cadmium is that cadmium is a fairly toxic element. So people are very afraid of using cadmium. And there are concerns about the availability of tellurium. Tomorrow we're going to be talking about critical materials. So there are some concerns with the mass production of these systems. The efficiency of cadmium telluride is around 17%. But again, the major concern with cadmium telluride is the fact that these materials may not be available, and these are toxic. So there are serious issues there. Same idea, you have glass on the top. This can be coated with an anti-reflective coating. Here you have your PN layer, cadmium sulfide, cadmium telluride to form your PN layer. And then you have aluminum in the back to collect your electrons. If you cut a cell and you look at the cross-section, this is what a cadmium telluride cell looks like. You have the bulk, which is cadmium telluride. Here you have your cadmium sulfide, a very thin layer. You have a glass substrate in this case. Then you have your metallic layer on the back to close your circuit. We talk about the SIGs, these copper, indium, gallium diselenide, very thin layer materials. In this case, they use molybdenum in the back. This very thin layer of molybdenum is deposited onto a glass substrate. You have a transparent conductive oxide. This is actually very interesting because if you remember on the silicon layers, you had these metallic lines on the top of the surface. Nowadays, we are using these conductive oxides. They are transparent, but they can conduct electrons. So we are using that top layer to let the radiation to go through, but also to close the electric circuit. So this is a major technology, having these conductive transparent oxides. And then you have your PN junction with cadmium sulfide and your SIGs in the bottom. These are becoming more and more effective. Your band gap, again, is around 1.04, so that gives you a slightly different part of the spectrum compared to silicon. And efficiencies between 12 and 14%. At the laboratory, they can do better, but in terms of mass production, that's what you get. Now, these are people believe that this is going to be the future of solar cells. Using these very inexpensive materials that you can apply by painting surfaces. They are called dye sensitized, and the idea of the dye is to pick up different colors that will help you tune the band gap of these materials. Again, the efficiency is not very high, but the cost is very low. So in principle, you can do this in high volume, and this could be easy to replace. The durability of this is not going to be very high because this relies on some organic materials. But nonetheless, there's a lot of interest just because this can be mass produced at low cost. And then finally, we have these multi-junction cells where now you stack, depending on how much efficiency you want, you can stack different cells or PN junctions through the thickness, with each layer picking up a different part of the spectrum. Now, this is the theoretical limit that we were talking about. This is the so-called Shockley-Queisser limit, and the reason why you can exceed this limit is because you are harvesting energy in different parts of the spectrum. So, who are the main players in solar technology? Obviously, China is a big player, and in fact, in the U.S., people were very upset because China was dumping photovoltaic materials into the market, and they were really taking people out of the market by dumping practices. So this has been a contentious issue with China. But Europe has been on a growing trend. There were policies talking about the importance of policies here in Spain with subsidies. Same thing in Germany, and there is a steady increase of that. We expect this to continue. Same thing in the rest of the world. But again, the big player here has traditionally been China. Japan was a major leader early on, but again. China now dominates the market. And the positive result of this is that as you mass produce these things, the costs go down. It's easier to introduce these technologies into the market. We all wish that they had better practices, but nonetheless, this is good news for the solar industry. Just to put things in perspective, this is 25,000 megawatts, 25 gigawatts. This is equivalent to 25 nuclear reactors. A typical nuclear power plants between 600 megawatts to 1,000 megawatts. So, put things in perspective, it's about 25 reactors. The U.S., we have 100 reactors, okay? And those 100 reactors produce only 8% of all the energy in the U.S. So this is when we show things in a logarithmic scale. This is good. This is actually great that there is a growing trend, but still we are orders of magnitude from where we would like to be, and hopefully there will be more opportunities for solar industry. In terms of installed capacity, Europe has been leading this for a while. Germany has the largest installed capacity with 17 gigawatts of generating capacity. That's pretty remarkable. Even in the U.S., it's just barely 2.6 megawatts. It's 2.5 nuclear reactors for the whole U.S. In China, even though they produce the majority of the photocells, the installed capacity is relatively small in China. So we hope that there will be a growing market in China for these materials. But give Germany a lot of credit. And it's really the result of public policies. Here is where a strong public policy, when they make a commitment to provide the necessary subsidies. So yeah, Germany has really set the trend there. Obviously, you get different results depending on where you are. What's interesting is that Germany is in one of these areas where the amount of solar radiation is not as great as what you will have in the southwest of the U.S. or in most parts of Africa. So because of that, I think Germany deserves even greater credit. Specifically in the U.S., there are some areas, the southwest, where they have ideal conditions to harvest sunlight. I mean, there's a lot of sun. Skies are usually clear. Humidity is low. And these could be areas where solar electricity production from solar will be good. So.